Hi all, thanks for coming. My name is Yasha Iravantchi, and today I'll be presenting Interferi. This work was done in collaboration with Zhang, Bernitsas, and advised by Mayank, Goel, and Chris Harrison. So one of the most immersive ways we can interact with computers is virtual reality. We can create these incredible new worlds, but very quickly it becomes lonely, and we want our friends to join us in these worlds. So naturally, social VR emerged as a way we can interact with friends online, but we want to interact with the environment in natural ways, such as communicating with hand and face gestures. While the controller can invoke hand gestures, what if we could do the same with no controller at all, leaving your hands completely free? So of course, we didn't get here overnight. There's a ton of amazing work that precedes Interferi. On the arm, they fall under four main categories: accelerometer-based methods, which instrument the hands and joints; geometry-based methods, which look for changes in contour contact; vision-based methods, which instrument the hands with cameras; and bio-based methods, which leverage physiological characteristics. Interferi falls into the last category. And on the face, we see similar categories, including geometry, vision, and bio-based. However, the main takeaway from all this is that gesture recognition is not a solved problem. And there's no one-size-fits-all solution. Systems that work on the hands may not work on the face, or vice versa. Additionally, smartwatch interactions may not work in VR, and the same way goes both ways. Interferi is our effort in tackling this problem. Our approach uses a single wristband for hand gesture tracking and a mask for facial gesture tracking. But before we go any further about Interferi, let's first talk about interferometry, the sensing principle itself. So let's start with a cylinder of water. This is a top-down view. We can add ultrasonic transducers all around the column of water. And then if we fire one transducer, seen in red, with a 40 kHz ultrasound signal, a sinusoidal wavefront is created. We can then take a second transducer, fire it in sync with the first transducer, and generate an interference pattern. Note the peaks in yellow that form constructive interference, and the troughs in blue form destructive interference. With our remaining transducers in blue, we can listen and capture the signal. But we can also move and shift interference patterns by changing the relative phase of the second transducer in purple. And we can change the phase arbitrarily, resulting in nearly infinite patterns from phase shift alone. But we can also pick any combination of transducers. We can move them around, or we can change the spacing of the transducers from one receiver in between to two receivers in between, and all the way to directly opposing each other. Again, we're always listening on the remaining transducers in blue. At the end of the day, we can produce literally an infinite number of patterns, despite the fact that we only have 8 transducers. So while this is all great in theory, we wanted to confirm in practice what interferometry looks like. So we filled an acrylic cylinder with water and placed two transducers at 90 degrees separation. We placed a receiving transducer on a CNC gantry, which allows us to move around the cylinder in a tight grid, allowing us to visualize the propagation of the signal in a bounded liquid medium. So this is the visualization of ultrasonic effects with a single transducer producing a wavefront. And this is the interference pattern with two transducers. Note the complex interaction between the two waves and the reflections off the wall of the cylinder. Of course, in the body, this is even more complex. There are high impedance boundaries like skin that create multipath interference, and anatomical features like fat, bone, and muscle that attenuate and scatter acoustic energy. These complex interactions are what makes the signal so unique, though, and it creates distinct features for machine learning. So in order to take advantage of this rich technique, let's discuss how we implement our system. So first, skin creates a high acoustic impedance barrier. It's hard to get signals into the body, and then it's hard to get them out again. So in order to do that, Interferi drives its transmitting transducers at 100 volts peak to peak. This allows us to inject a robust signal into the body and still have enough acoustic energy to bounce back out again. Second, the speed of sound in the body is about 1,500 meters per second. So for on-body interferometry to work, it requires tight sub-degree synchronization across all of its transducers. So Interferi achieves about a 0.1 degree tolerance. And lastly, interferometry requires a high sampling rate. Since our carrier wave is 40 kilohertz, we need to sample at way, way higher speeds. And Interferi samples at 480 kilohertz. What's particularly cool about Interferi is that the last 2 points we were able to run this off a hacked TNC 3.6. We really wanted to use commodity hardware as best as we could, and so we don't really want to reinvent the wheel. So for the arm, we designed 4 armbands along 2 design axes and selected one that arranged 8 transducers around the digitorum muscle. And on the face, we designed 4 masks across 2 axes and selected one with 8 transducers symmetrically around the eyes. For more details as how we came up with our final 2 form factors and transducer pair combinations, please see the paper. And this is what our final 2 wearables look like in real life. So let's actually see how interferometry works. So I have my armband over here. And then as you can see, like as I have my arm, as I move it, the signal is really changing with my hand. So let's actually train this. So as you can see, with just one instance of training, it works. So to evaluate our system, we use 2 gesture sets, one for the arm, which we adopted from Tomo, a previous work, and one for the face. I had this video originally to prove to you that it actually does work. So this is live recognition of it working, but I see you guys saw it in real life. And then on the face, we have the laptop showing the same signal, showing gestures that include neutral, left eye closed, right eye closed, both eyes closed, eyebrows raised, smile, frown, mouth open, and my favorite, kissy face. So to evaluate the performance, we ran a user study. We recruit 10 participants, and they were asked to perform each gesture in a random order so that no gesture was performed back to back. Each full set of gestures formed a round, and we collected 10 rounds of gestures to form a session. In between each session, the worn sensor was removed and reworn to evaluate how robust our system was to positional changes and over time. On the machine learning side, we used scikit-learn's random forest classifier. To evaluate the within-session performance, we performed a leave one round out cross-validation, where we trained on 9 rounds within a session and tested on the 10th all combinations across both sessions. We found that Interferi performs well across the 11-class arm gesture set at 93% across all users. Looking at the hand gesture subset in purple, Interferi performs particularly well at 98%, and it also performs well with the pinch set in orange at 90%. So cross-session accuracy is when training the system on one session's data and testing on data that was collected at a different time when the band was removed and reworn. Interferi has a classification accuracy of 65% across the entire gesture set and 80% on the hand set. What this suggests to us is that some gestures, such as stretch and Spider-Man, are much more robust to changes in armband positioning. On the face, we found that Interferi performs well across the 9-class face gesture set with 89% across all users. And for the eye and mouth subsets, we found that Interferi performed at 92% and 91%. Similarly, Interferi has a cross-session accuracy of 64% across the entire gesture set, but similar to the arm, certain gestures are particularly robust across sessions. However, more challenging than discrete gesture recognition is continuous tracking. This is the most atomic stage of gesture recognition, as it can generate other gestures. So for continuous tracking, we recruit 10 participants, and we ask them to perform 4 tasks. 1 is the degree of smile task, 2 hand pose, 3 wrist angle, and 4 weights. For the hand pose and wrist angle tasks, we use the leap motion as ground truth. And for regression, we use scikit-learn's extra trees regressor. So for the continuous tracking degree of smile task, we asked users to perform 4 different levels of smile, from neutral to big smile. And our average smile intensity error was 8.6%. For the hand pose task, we asked the users to close their hand and close their thumb. And we found that the average error was 1.7 degrees for the thumb and 6.5 degrees for the 4 fingers error. And in the plot below, you can see on the thumb and 4 fingers that Interferi tracks reasonably well with the leap motion. For the wrist angle task, we asked the user to move their hand all the way to the left and all the way to the right. And the average wrist angle error was 5.3 degrees. And similarly, Interferi tracks well with the leap motion. And for the last task, we performed a weights recognition task where the participant was asked to hold 1 of 5 weights. In this task, we performed a leave 1 weight out evaluation, where we train on 4 weights and test on the 5th, all combination. What this means is that machine learning is attempting to predict on a weight category it's never seen before. So this includes scenarios that require extrapolation, such as training on 0 pounds, 6 pounds, 9 pounds, and 12 pounds, and then asking it to predict 15. And we found a leave 1 weight out error of 1.59 pounds. So finally, Interferi does have some limitations. The first is that it requires per user calibration. So I can train on myself, but it won't work if I put it on someone else. Interferi also currently requires large transducers. So while we can use smaller transducers, we don't have a guarantee that the signal will be as robust. And Interferi also relies on good acoustic coupling. Form factors do need to ensure good contact conditions. So to address those 2 previous limitations, in the future, better housing ergonomics and conformity could improve performance. On our worn form factor designs, they were designed as a one-size-fits-most, so those with larger or smaller arms and faces didn't have good contact conditions with the wearable. So we see Interferi being quickly integrated into existing wearables that can conform to multiple body sizes, such as on the left. On the right, we have some mock-ups integrating Interferi into a potential Apple Watch band or within an Oculus DK2. That was Interferi, and thank you for coming.
So we have 5 minutes for questions.
Hi, Louis Chong from LMU Munich. That was a fantastic talk. Thank you for the live demo. I'd just like to ask a couple of questions about the extent to which Interferi might either interfere with other possible devices or other sensors or on-body sensors like electrodes, for example, and vice versa. What might be environmental variables that might interfere with your signal itself, such as ambient sound, or if that's even a factor?
So the kind of cool thing about these transducers is that the metallic shell is the ground pin. And so you can actually create a hybrid system that pairs something like Tomo, and you can use electric impedance tomography in real time at the same time as Interferi. So you can drive an electric system that won't interfere with my acoustic interferometry system. You can have hybrid models that also vote between like Tomo system and my system, and then you can create an even more robust gesture recognition system. Does that answer? Okay.
Thank you. So Feng Yuan from University of Toronto. So just a quick question. So what is the latency level of your whole system? Like it's a couple of milliseconds or something like 100 milliseconds after the gesture itself? Thank you.
So our system runs pretty real time. I think if I recall off the top of my head, we were running at 50 frames a second. So 1/50th of a second would be the latency.
Okay, thank you.
Hi, Adam Agassi from the IDC Media Lab in Tel Aviv, Herzliya. What machine learning algorithm do you use for the training and for the recognition?
So for discrete classification, we use scikit-learn's random forest classifier, default parameters with 200 trees. For the regressor, we use an extra trees regressor in scikit-learn, default parameters, 200 trees. The kind of interesting thing about Interferi is that all the other algorithms worked as well. So SVM worked. I think we also ran it on k-means as well, and that worked as well. Like the signal is robust enough that it's pretty clear to any machine learning algorithm.
I have one question. Is there any interference with sweat?
So the reason why we go to 100 volts is because it basically kind of punches through everything. One of the big problems with biosensing systems is that there are a lot of interferences. There's arm hair, there's sweat, there's different fat composition, muscle composition. So in order to overcome all of that, we went to 100 volts so that we just have a robust signal all the time.
Thank you.
One question, you just mentioned like the 100 volts. Is there any implications that this is harmful in any ways to the body?
So in terms of like electric shock, we current limit everything. So all of our transducers are also very high impedance, so there's not much current that's traveling through it. This is actually a very low power system, just high volts. In terms of the harmful effects of ultrasound, there's been many studies that show that ultrasound does not have harmful effects on the body, except for when you turn into like military applications, but that's not what we're doing here.
Thank you for your presentation. And simple question. Your system can discriminate between the one finger and the two finger?
Our system, so like being able to like do pinches? Yes. So I think I might have gone through that a little too quickly. But so, in addition to being able to do full hand gestures, we can also do individual pinches.
A pinch?
Yep. So those are our pinch gesture sets.
Like moving the 1 and 2?
Yes.
Also this one and this
yes,
one.
we can do that. We just didn't evaluate that in our paper.
Okay. Thank you.
We have one question here.
Hi, I'm Zhang from Dartmouth. And do this device have a specific placement? I mean, maybe different placements and different accuracies.
Could you repeat the question? It's a little.
Okay. My question is, does this device have a different accuracy based on different placements? I mean, maybe different placements have a different accuracy.
So we found that, for instance, in our weights error classifier, people who had difficulty holding the 15-pound weight, their accuracies were lower. It's a function of, one, like how well can you perform the gesture or how well can you hold up the weight. It's also a function of like, does this armband fit your arm or not? It's really, really hard to fit this on people who have really small arms or really large arms.
Could you show us the results of the classifier? Because from what I saw, there's a huge difference between left eye and right eye pinch. Left eye and right eye.
Yep. So in the across or?
Yeah. So left eye closed is about 90% accuracy.
Yep.
And right eye closed is about 60%. And to me, this looks like, to me, it would be like almost the same.
Yeah, so this is what's kind of interesting is that we noticed that in some gestures that are asymmetric, like left eye closed, right eye closed, people who are more comfortable with, like most people regularly will wink with their right eye instead of their left eye. And so when they're performing a left eye closed task, they will perform it a little bit stronger than they would a right eye closed. So that's why when the gesture itself is being performed with more force, it's going to have a more distinctive signal. So that's why there's that asymmetry there.
Nice presentation. Thanks for the presentation.
Simple question. What is the advantage of acoustic sensing over EMG? Did you do any comparison?
So EEG has, EEG is kind of one of those things where...
EMG.
EMG?
Yeah.
So EMG has more contact condition issues than acoustic sensing would. For instance, EMG is much more sensitive to sweat, or much more my arms would have a difficult time putting EMG because I have hairy arms. So I don't necessarily want to shave my arms in order to use the system. This system would work on people with different hair conditions as well. Also, this is a completely dry system. There's no gel, there's no paste that's on there in order to produce the coupling. So this system, I put it on and I would put it off, and there's nothing I have to wipe off my arm.
Sorry, with the same question, because there is this off-the-shelf system called Mio. Did you compare your system with their system? Because it's more or less, it just looks the same. The technology is different, but it would be really interesting to have a comparative study about it.
Yeah, so there's a lot of systems that we could have compared to, but we chose to compare to a system like Tomo more directly. Okay. There's a lot of different ways to evaluate gestures within the gesture sensing community, and this is the way we chose to evaluate it. But that could be another way that in the future people could evaluate the system.
Yeah, okay.
Okay, so let's thank all our speakers and... If you want to continue talking to them, there is a coffee break now in Hall